Question number 6. If y is equal to e raised to the power x sin x, then show that second derivative d2y by dx square minus 2dy by dx plus 2y is equal to 0. Solution: we have y is equal to e raised to the power x into sine of x. So first we find first derivative by using product rule. Differentiate with respect to x. So dy by dx will become e raised to the power x will be as it is, and derivative of sin x plus sin x will be as it is. This is actually sin x, and derivative of e raised to the power x. So first derivative dy by dx will become e raised to the power x, and derivative of sin will be cos x, and sin x will be as it is, and derivative of e raised to the power x is e raised to the power x. Taking e raised to the power x as a common factor, we have cos x plus sin x. Now again differentiating with respect to x. So the left hand side will become a second derivative, which is d2y by dx square, and again we have two terms. First one is ex and the second one is cos x plus sin x. To differentiate, we have to use our product theorem. E raised to the power x will be as it is, and derivative of cos x plus sin x plus cos x plus sin x will be as it is, and derivative of e raised to the power x. Now e raised to the power x will remain same, and the derivative of cos x will be minus sin x, and derivative of sin x will be cos x. This cos x plus sin x will be as it is, and derivative of ex will be ex. Again we can take e raised to the power x as a common factor. So the remaining part will be minus sin x plus cos x plus sin x. So d2y by dx square is actually again e raised to the power x. This sin x and this sin x will be cancelled out. We have second derivative 2 e raised to the power x into cos of x. Taking d2y by dx square minus 2dy by dx plus 2y. So just putting the values, d2y by dx square, which is 2 e raised to the power x cos x. This minus 2 will be as it is, and dy by dx, the value is this one, and 2, and the value of y is e raised to the power x sin x. Now 2 e raised to the power x cos x, 2 minus 2 e raised to the power x cos x minus 2 e raised to the power x sin x plus 2 e raised to the power x sin x. So these all values are cancelled out. 2 e raised to the power x cos x and 2 e raised to the power x sin x. Finally we have our required proof, d2y by dx square minus 2dy by dx plus 2y is equal to 0. So this in this question we just first find first derivative and then second derivative, and by taking this one try to prove this left hand side is equal to 0. So just putting the values of second derivative, first derivative and the given y, and then simplifying this one, that leads to the required result, which is 0. Almost same question, question number 7. Y is equal to e raised to the power ax into sine bx. Show that second derivative d2y by dx square minus 2a d2y, this one is actually dy by dx, plus a square plus b square y is equal to 0. Solution: that y is equal to eax sine bx. Differentiate with respect to x, dy by dx by using product theorem. First one is as it is, and derivative of second one, and then second one is as it is, derivative of first one. So just simplifying this one, or using formula of differentiation of trigonometric function, derivative of sine will be cos bx, and then derivative of this angle will be b. Sine bx will be as it is, derivative of e raised to the power ax. As we already know, the derivative of exponential function is just e raised to the power ax, and then to differentiate this value ax, the derivative will become just a, because derivative of x will be 1. Now e raised to the power ax being a common factor, we have b cos bx plus a sin bx. Again differentiating with respect to x, second derivative d2y by dx square, and on right hand side again using a product theorem, e raised to power ax will be as it is, and then derivative of this one, b is a constant term, derivative of cos is minus sine bx, and then derivative of this bx will be b. Similarly, a will be as it is, derivative of sine bx will be cos bx, and derivative of this angle bx will be b, plus this b cos bx plus a sine bx will be as it is, and derivative of this e raised to the power ax will be e raised to the power ax into a. Again we can take e raised to power ax as a common factor, so the remaining part will be minus b square by multiplying this b to b, b square sine bx, a into b, ab cos bx, this b cos bx by multiplying this a will be ab cos bx, and then a square sine bx, minus b square sine bx, ab cos bx, and ab cos bx will be 2ab cos bx, and this a square sine bx will be as it is. Again taking left hand side, d2y by dx square minus 2a dy by dx plus a square plus b square y, and putting the value of this second derivative, this first derivative, and this y, just putting the values and then simplifying, this e raised to power ax multiplied to b square sine bx is this one, this e raised to power ax by multiplying 2ab cos bx, and again e raised to power ax by multiplying a square, we have sine eax, a square sine bx, this is b square sine bx, and by simplifying this one, these all terms will be cancelled out. We have only d2y by dx square minus 2a dy by dx plus a square plus b square into y is equal to 0. As we can simplify this one, this minus eax b square sine bx will be cancelled out to this plus eax b square sine bx, this 2eax ab cos bx, and this 2 e raised to the power ax ab eax cos bx, and similarly this sine bx will be cancelled out to this sine. So finally we have only this 0 on right hand side, which is our required proof. Question number 8, we have y is equal to cos inverse x whole square, then prove that 1 minus x square y2 minus x y1 minus 2, this y2 is second derivative, this y1 is first derivative. Solution, let y is equal to cos inverse x whole square, differentiate with respect to x, differentiate with respect to x, we have y1 by using power formula 2 cos inverse x, and then derivative of this inner function, which is minus 1 under root 1 minus x square. So this one is actually derivative of cos inverse x. 1 minus x square square root can be multiplying to left hand side y1, and on right hand side we have minus 2 cos inverse x. Squaring on both sides, we have 1 minus x square y1 square, and on right hand side we have 4 cos inverse x whole square. As we know that cos inverse x whole square is just y, so we can replace this value by y. So we have 1 minus x square y1 square, and this whole thing will become y. Now to find second derivative, again differentiate this one, differentiate with respect to x. This 1 minus x square will be as it is, and derivative of y1 square will be 2 into y1, and then derivative of y1 will be y2, plus now y1 square will be as it is, and derivative of 1 minus x square will be minus 2x, because this one is in form of product. So using product theorem, first one is as it is, derivative of second one, then second one is as it is, and derivative of first one, which is minus 2x, and on right hand side we have 4 as a constant term, and derivative of y will become y1. This 2y1 can be taken as a common factor. We have 1 minus x square y2 minus x y1 is equal to 4y1. This 2y1 can be divided, and we have 1 minus x square y2 minus x y1 is equal to 2, and finally 1 minus x square y2 minus x y1, this 2 can be shifted to the left hand side, minus 2 is equal to 0, which is our required proof. Question number 9, if y is equal to a cos log x plus b sin log x, then prove that x square d2y by dx square plus x dy by dx plus y is equal to 0. Solution: y is equal to a cos log x plus b sin log x. First derivative dy by dx, and derivative will apply on right hand side separately, both of these two terms. A will be constant term, cos log x, the derivative will become minus sin log x, and then the derivative of this angle log x will be 1 over x, plus similarly b is the constant term, derivative of sin will be cos, and this is an angle of cos x, so then differentiate this angle will become 1 over x. This 1 over x is the constant common term, so we have minus a sin log x plus b cos log x divided by x. Now again differentiating with respect to x, differentiate with respect to x. This is actually in the form of quotient theorem or in the form of fx over gx, so we can differentiate this one by using our quotient theorem. In the denominator that will become x square, and this x will be as it is, derivative of this numerator, and then minus numerator will be as it is and derivative of denominator, which is just x. So just to simplify this one by taking derivatives, first we shift this x square to the left hand side, so left hand side will become x square d2y by dx square, and on right hand side we have this x. Again using the same process in the steps above, we have derivative of cos log x, which is sin log x, and then derivative of log x will be 1 over x. So this one is actually the simplification of this step. Minus sin b sin log x into 1 by x minus a cos log x, derivative of log x will be 1 over x, and the next term will be b cos log x minus a sin log x, and derivative of x will be 1. This 1 over x can be taken as a common factor. We have a cos log x plus b sin log x. This minus is also a common factor. Minus this one is remains same. The second term will be remain same. So simplifying this x to x, we have our third equation, minus a cos log x plus b sin log x minus b cos log x minus a sin log x. From 2, we can write it as b cos log x minus a sin log x is equal to a x dy by dx, which is in the previous slide. So putting 1 and 4 in 3, the value using 1 and 4 we can put into the equation number 3. This a cos log x plus b sin log x and this b cos log x minus a sin log x will become, left hand side will be as it is, x square d2y by dx square. This is actually the given expression, which is y, and this one by using 4 we have b cos log x minus a sin log x, which is written as x dy by dx. So this will become minus x dy by dx, and this will become only y. So both terms can be shifted to the left hand side, and that will become x square d2y by dx square plus x dy by dx and plus y is equal to 0, which is our required result. So hence proved.